Welcome to our 1.2 video here. We're going to be talking about reflections and stretches. What this means is we are going to be taking some graphs and reflecting them across either the X or Y axis like it's a mirror. We are also going to be taking graphs and stretching them vertically or horizontally, or compressing them, squishing them horizontally or vertically. So this first graph here, we're going to graph something we are familiar with. In Precalc 11, you covered lots of quadratics. We are going to graph f of x equals x plus 2 squared. So just a reminder, this is a quadratic with a vertex at -2, 0. It opens up and it has our most basic pattern. Okay? So we're going to put a point at -2, 0. And we go over 1, up 1, over 1, up 3. We could go over 1, up 5, but it would go off of our graph here. Okay, so this is our f of x. We want to determine f of -x. Okay? This means anywhere I had an x inside my function, I need to replace with a negative x. So my new function is going to be f of -x equals -x plus 2 squared. So x is mapping to -x. And what this means is anywhere we had an x in our function, we must replace it with -x. So we're going to try and graph this. It says to sketch it on the same grid. So if I plug in some numbers, we can figure out where this would go. The whole point of learning the rules here is that we won't have to plug in numbers once we figure out what the rule is. We can just look at our original graph and flip it wherever it's going to flip. But for now, if I plug in, say, 0 here, if I plug 0 in for my x, I would get 0 plus 2 squared, or 2 squared, which is 4. So you can draw yourself a little table of values off to the side if that helps. But if x is 0, y would be 4. Okay. Now what if we plug in, say, x is 1? If I plug in x is 1, I'm going to get -1 plus 2 all squared, or 1 all squared, which is 1. So when x is 1, y is 1. This looks promising. If I go to the left, I'm probably going to be getting higher y values, so I'm going to keep going over to the right. If I use a positive 2, if I pick x is positive 2, in my function I'll have -2 plus 2 all squared, or 0 all squared, which is 0. Okay, let's keep going to the right. I'll pick 3. If I plug 3 in, I get -3 plus 2 all squared, which would be -1 all squared, which is 1. And you can already see the pattern of the parabola forming. We know parabolas are symmetric, so I know my next point has to be right here at a y value of 4. Again, if I kept going to the left and the right, I can see that my basic pattern here has not changed. My vertex is right here at 2, 0. I've gone over 1, up 1, over 1, up 3. My next one would be over 1, up 5, which would go off the grid, so I'm going to connect these. And this would be our f of -x. So as we can see, this looks like our whole graph has flipped across the y-axis. This is called a horizontal reflection because all of our x values have changed, but you can see I still have all the same y values. I have a y is 0, I have 2 y's at 1. I have 2 y's at 4, but all my x values here are different. Okay? So this one is a horizontal reflection. Or we can say it reflects across the y-axis. The y-axis is acting like our mirror here. In the textbook, you might also see it might say in the y-axis instead of across. It's the same thing. Okay? If the y-axis is what you're flipping across, okay, that is a horizontal reflection. So I'm sure you can probably predict what will happen for the next one. Okay? If I'm determining negative f of x, this means that f of x is mapping to negative f of x, which means anywhere we had an f of x, we are going to replace with a negative f of x. So what that means is ours negative f of x is going to be negative x plus 2 squared. And you have actually graphed things like this before. The negative in front, reminder, that tells you that your parabola is upside down. So this would be a parabola with a vertex of negative 2, 0. But it opens down. So my vertex is in the same spot as the black parabola was, but now I'm opening downwards, so I'm going to go over 1, down 1, over 1, down 3. I could keep going over 1, down 5, but I would run out of space on my grid. Connect my points. This would be negative f of x. So basically, if you have the negative in front of the function, this is a vertical reflection. Or we can say across the x-axis. So the x-axis is acting like your mirror here. So again, you can see that all the x values are the same. I have an x at negative 2. I have 2 points when x is negative 1. I have 2 points when x is 0. I have 2 points when x is negative 3. 2 points when x is negative 4, but all my y values are different. So in general, when x is replaced with a negative x, then the graph is reflected across the y-axis, or a horizontal reflection. Okay. We think of that as f of x being mapped to f of negative x, or x being mapped to negative x. When y is replaced with a negative y, or f of x is replaced with a negative x, then the graph is reflected across the x-axis, which is a vertical reflection. Now, similar to how in the previous lesson we said a horizontal translation or a vertical translation could be written as HT or VT, horizontal reflection can be HR, vertical reflection can be VR. Okay. And the mapping for this one is that f of x maps to negative f of x. Okay. So the reflections, once you know which ones are which, are not too complicated. You're basically just flipping all the points in your graph. So the horizontal reflection, you're going to flip all your x values. So if you had a negative 4, now you're going to have a positive 4. Okay. For the vertical reflection, you're flipping all the y values. So if y was originally 5, now y will be negative 5. So the next one that we're going to look at is to stretch or compress a graph. So we have the graph here of our basic absolute value function, which is y equals the absolute value of x. And if the point graph is too light for you, you can, if you've printed it off, you can make it a little darker if you'd like. Okay. So we're going to try graphing these two different things, and we are going to look at them through a specific lens. So this first one here, we have a 2 inside the function with the x. We're going to create a new table of values for this. So if I plug -4 in here, I get y equals the absolute value of -8. Remember, an absolute value turns everything positive, so this is actually going to be +8. If I plug -3 in, I get the absolute value of -6, which is going to give me +6. Then -2 gives me absolute value of -4, which is 4. Then 2. If I plug 0 in, I get the absolute value of 0, which is 0. If I plug 1 in, I get absolute value of 2, which is 2. Plug 2 in, I get absolute value of 4, which is 4. And I have 6 and then 8. So if I want to graph this, I've got a point at 0, 0. I've got a point at 1, 2. I've got a point at 2, 4. I've got a point at 3, 6. And 4, 8. And this reflects on the other side. And I can connect those points. Okay. Now, specifically, we are going to be looking at this through the lens of what happened horizontally. The reason we are doing that is because the 2 is inside the function. So as with yesterday, if we added or subtracted a number inside the function with the x, that was a horizontal translation. Just on the page before, if the negative was inside the function with the x, that was a horizontal reflection. Here, if we have a number inside the function with the x, that is going to be a compression or a stretch horizontally. Okay? If our number was outside of the function, that would be a vertical stretch or compression. So if I'm looking here at what happened to corresponding x values, for example, when x is 4, on my original graph, I have a point right here. Okay? Where did that point move to? That point moved over to the left. What happened to my x value? My y value stayed the same. We're trying to compare from similar points what happened to the x values here. So here, my x value at my new point corresponding to that, my x value is 2. So my x actually cut in half. Okay. What happened to this one here? This one here is at -1, 2, 3, 4, 5, 6. It moved over here. This one is at -3. My x value cut in half. So for all of my points, that will be true. I could take this one here. The original point is at 2. It moved in and is now at 1. My x value cut in half. All of my x values for the corresponding y value of my original function, all my x values are cut in half. Okay. Okay. All my x values are half as big. So what we read this as is a horizontal, because it's x that's changing, expansion or compression by 1/2. Okay. Normally we can use the word expansion for anything, but some people find that a bit confusing. So you could say this is compressed or squished by a factor of 1/2. All of our x values were divided by 2 or multiplied by 1/2. So just a reminder, dividing by 2 and multiplying by 1/2 are the same thing, right? If I take 10 and I multiply by 1/2, I get 5. If I take 10 and divide by 2, I also get 5. So all of my x values have been divided by 2 or multiplied by 1/2. We read that as a horizontal expansion by 1/2. This is our short way of writing that. I'm going to erase all the red stuff because we're going to do another one. So if I take a look at the next one, I have a 1/3 inside the function with the x. This means we're going to look at this from a horizontal lens again. Okay. So if I take the first one, the first one's not going to be that nice. I get -4/3 inside my absolute value, which would give me 4/3. I might not want to plot that one. If I plug -3 in, I get -1 inside my absolute value, which gives me +1. Then I'm going to get 2/3 and then 1/3 if I plug those next x values in. If I plug in x is 0, I get a y value of 0. If I plug in x is 1, I would get 1/3. If I plug in x is 2, I get 2/3. If I plug in x is 3, I get the absolute value of 1, which is 1, and then I would have 4/3. Okay, so I'm going to again plot the nice points. I'm going to have a value at 0, 0. I have a coordinate at x is 3, y is 1. X is -3, y is also 1. Now, this is not really enough to graph this nicely, but the thirds are not nice to graph either. So what I would choose to do is figure out what other x value would result in a nice y value. So I would pick x is, say, 6. If x was 6, y is going to be the absolute value of 2, which is 2. So I'm going to put a point over when x is 6 and y is 2. The same thing will happen if x is -6. I'm going to get the absolute value of -2, which is also 2. Excuse me. Sneeze there. Okay, let's connect those. Okay, so again, we're going to look at this from a horizontal lens because the 1/3 is inside the absolute value. It's inside the function with the x. So for example, if I take a look at this point here, where did it move to? It moved over here. Originally, it was at 2. Now it's at 6. If I take a look at this point here, it moved over here. Originally, it was at 1. Now it's at 3. -1 to -3. So we can see that these x values have been multiplied by 3. Okay? The x values are 3 times as big. So this is going to be a horizontal expansion by 3. All of our x values were multiplied by 3. So for the blue one, all of our x values were multiplied by 1/2. For the purple one, all of our x values were multiplied by 3. And if I look at my function and try and figure out, okay, so how would I tell how much I'm going to multiply by? My first one, the blue one, I had a 2 inside the function with the x, and my expansion was by 1/2. For the purple one, I had a 1/3 inside the function with the x, and I actually multiplied by 3. So again, the x's are a little bit counterintuitive here because if it says 2, we're not multiplying by 2. We're actually multiplying by 1/2. If it says 1/3, we're not actually multiplying by 1/3 or dividing by 3. We're multiplying by 3. So we are actually always expanding horizontally by the reciprocal of the number inside the function in front of the x. So if I had a 5 inside the function in front of the x, I'm actually going to multiply by 1/5. Okay? So this is why I wanted to look at the horizontal values and this situation so that you could see that The number inside the function in front of the x is not what you will multiply by. You're going to multiply by the reciprocal of that. Vertical ones are much easier. Whatever it is what you do. If I have a 2 in front of the entire function, I'm going to multiply all my y values by 2. Okay. So I'm going to write down your general rules here. Okay. Let's start with the horizontal one because that's what we just took a look at. So when f of x becomes f of bx, so you have something inside the function in front of the x, this is going to be a horizontal expansion or compression. Okay. So we're going to take our existing x values and multiply by 1 over b. Okay. So if b is greater than 1, this is actually going to be a horizontal expansion compression by 1 over b, which if we had, say, a 4, that means it's going to be an expansion compression by 1 over 4. Most people find it easier to think about that as a compression. Everything's getting smaller. So if your b is bigger than 1, all your x values are going to get smaller. Okay. So for example, if we had y equals f of 4x, this is going to be a horizontal expansion or compression by 1 over 4. What this means is we're going to take every x value, multiplied by 1 over 4. Okay. And a reminder again, that's the same as dividing by 4. Okay. So if I was given a graph, okay, I might not have even been given a function. So I might not be able to make a table of values. So let's say I was given a graph. So I'm going to just scroll back up here for a minute. I'm going to erase some stuff, and I'm going to show you a bit of a shortcut. So let's say I wanted to draw the one that we just talked about. We said, let's say y was equal to f of 4x. Okay? This would be a horizontal expansion by 1 over 4, meaning x values need to divide by 4 or multiply by 1 over 4. So I would want to pick x values that can easily be divided by 4. So I probably want to pick where is my x4 and where is my x8 to start. Okay, there's where x is 4 and x is 8. So what's going to happen is my y values will stay the same. Only my x values will be divided. So if I take this first coordinate is at 4, 4. I divide the x value by 4, I would get 1, which means this point is going to move over to where x is 1. The y value would stay the exact same. So now this point is going to be at 1, 4. If I take when x is 8, this point here is at 8, 8. If I divide the x coordinate by 4, I would get 2. So this one's going to move over to the left to where x is 2, and now my coordinate would be 2, 8. Okay. So these don't move, these points don't move up or down here. All I'm doing is dividing all my x values by 4. If I take the origin, 0, 0, if I divide the x value by 4, I still get 0. So that point is not going to move. And I could now connect these points this way. And I could do the same thing on the other side. When x is -4, now what's going to happen is it's going to move over to be -1. When x is -8, it's going to move over to be -2. And I can connect those. So I don't need the table of values. So the whole point of learning these rules is once I have to do all the transformations at once, making a table of values is going to be very tedious. Also, you are not always given the actual function to make a table of values with. Sometimes you are simply given the graph. You have no equation to work with. You cannot make a table of values. So if you don't know the rules of how to get there, you can't go from the graph of the original to the graph of the new one. Okay. So the last one is if b were between 0 and 1, so if it's a fraction, there is a horizontal expansion by 1 over b. But on this one, because b is a fraction, your x values are going to get larger. So for example, if you have y equals f of 1 over 7x, this is actually a horizontal expansion by 7. So every x value multiplied by 7. So what we just did in the little example we did above was we took all the x values and divided them by 4. We picked things that were nice and easy to divide by 4 so that we had nice new points. Here we could take any x value and multiply by 7. Again, don't pick something too big. I'd pick something like 1 or 2. You might even want to take something like a half and multiply it and have a new point at 3.5. That's okay. But you would take all your x values from your graph, multiply them by 7. And so what's going to happen is your graph's going to get wider because all your x values are spread more apart and out farther than they were. Okay, so if I did the same thing as I just did up here, if I took all my x values and multiplied by 7, okay, if I'm at the origin, my x coordinate is 0. If I multiply by 7, nothing happens. It's going to stay the same. But if I take this one here, where x is 1, if I multiply by 7, now I'm at 7. Now I'm way out here. So when I connect this, it's going to go way out like this. So it's like I've taken that point and stretched it outwards, horizontally stretched it out. Okay. So next we'll take a look at what happens if f of x becomes a f of x. So you have a number in front of the whole function. And this one is going to be a vertical expansion or compression. Okay. So you're going to take your y values this time and multiply by a. Okay, so if a is bigger than 1, that is going to be a horizontal or a vertical expansion. By a. So your y values will get larger. So for example, if you have y equals 5 f of x, this is a vertical expansion by 5. So we would use VE instead of HE. And this just means every y value is going to multiply by 5. So again, if I go back to my absolute value graph up here and I take a look at what would happen. Okay. If I look at the origin, y is 0, times by 5, still 0. If I take a look at this point here, y is 1. If I times by 5, now my y would be 5. my x value would stay the same. So this point is just going to move up. Okay. The next point, y is 2, so now y would be 10. So it's actually going to be off our graph here. So it just moves up. Okay. So it's expanding. It's being multiplied by 5. Okay. And then we would connect those points. Doesn't want to erase. Okay. So the key here is that if I'm doing a vertical expansion, my x value stays in the same spot. My point just stretches up higher than it was before. My y value gets bigger. Okay. The last one, if a is a fraction, okay, this is going to be a vertical compression by a. Your y values are going to get smaller. So for example, if I have y equals 1 over 4 f of x, this is going to be a vertical expansion by 1 over 4. I'm going to take, what's going on here? I'm going to take every y value and times it by 1 over 4. Remember, that's the same as dividing by 4. Okay? So all my y values would get smaller. Okay? So again, I would probably pick things that I could divide by 4 nicely. I'd probably pick, where do I have a y value of 4? If I divide by 4, my new y value would be 1, but my x coordinate of that point would stay the same. So tomorrow, or for the next lesson, what we're going to be doing is taking all of these things and doing them together. So we might have to expand or compress, flip, and move left, right, up, down. For your practice questions today, you might have to do a vertical expansion at the same time you do a horizontal one. All that means is if your original x coordinate was, let's say, 2, 3, that 2 and the 3 would both change if you are doing both a vertical and a horizontal expansion or compression. So what that would look like as a function is you'd have a number in front of your function, but you would also have a number inside the brackets with the x. So make sure you do lots of practice for these first 2 lessons, because doing the third one will be very difficult if you can't do these skills in isolation. You'll have a very hard time putting it all together.